Let's talk about colligative properties. First of all, it's one of my favorite chemistry terms, colligative. Say it with me. Oh, that was kind of wimpy. Colligative is what people, is that a toothpaste? No, it is not. It is a physical property of a solution, and it depends on the number of dissolved particles, not on the identity of the particles. The properties that are affected are vapor pressure, which is always lowered, boiling point, which is always elevated, and freezing point depression, which is, freezing point's always depressed, and the osmotic pressure. This is what's going on. You are meant to believe that this is a beaker, and this is a beaker that is containing nothing but pure solvent. Let's say it is water. Now, this pure solvent is going to evaporate. Those gas particles are going to rocket around. Some of them will strike the surface of the liquid, causing a pressure that you know as vapor pressure. All right, if you add a non-volatile solute, what is non-volatile? It doesn't evaporate, okay, and I will depict those with X's. The non-volatile solute particles actually block the surface of the liquid and allow fewer particles of the solvent, water, to evaporate. Get that? If you are able to reason that out, you got this whole thing sorted.
Wait, one more time.
Okay. The non-volatile solute particles are actually a physical barrier for the solvent particles to evaporate. They're in the way. So the vapor pressure,
Would it be like salt water or not?
sorta. I'm gonna always. Yep. I will show you something about salt water in just a second. Okay. This, if you look carefully, you will see that this is one cheek of the butt diagram. Got it? Here's the liquid, here's the gas,
Where's that angle?
and here is the vapor pressure of the pure water. Okay. When you add a non-volatile solute, the vapor pressure of the solution is decreased. Okay, this stuff will make sense to you in a little while. Maybe not now. All right, so in words, this is what I just said with a picture. Okay, so the vapor pressure is lowered because the non-volatile solute is in the way. All right. The extent to which a non-volatile solute lowers the vapor pressure is proportional to the concentration of the non-volatile solute. That just makes great sense. If you have this many particles of the non-volatile solute, it will block so much. If you triple the number, it's going to block 3 times as much. Now, what is important to know, it does not matter what this is. It just matters how many particles there are. Okay. So this whole thing can be mathematically expressed using Raoult's law. Really, that's how you say it. How would you say it?
Routes.
Raoult's? No. Raoult.
Raoul.
Raoult's law. Thank you. Raoult's law is this, and you might need this little crutch for a little while. The vapor pressure of the solution is equal to the mole pressure of the solvent. Circle that because this is a new thing for you. We're using the mole fraction of the solvent, which you recall is the moles of the solvent over the moles of the solvent plus the solute. Okay, the mole fraction of the solvent times the vapor pressure of the pure solvent. P aught is the vapor pressure of the pure solvent. Okay. Now, we need to talk about the number of particles that something can put into solution. Oops, my little thing is in the way. The number of particles that can be put in a solution is called the Van 't Hoff factor. It has the, looking at you, I'm going to be irritated if you close your eyes. It is I. So here's what we're talking about. If you have NaCl in solution, what will happen to it? Into?
Na plus ions, Cl minus ions.
An Na and a Cl. 1 mole of NaCl yields.
1 mole NaCl.
And okay, so 1 mole of NaCl yields 2 moles of particles, right?
Yeah.
All right. So if you had this, it does not ionize. 1 mole of this will give you 1 mole of particles. Okay. So let's see if you are awake ski. The Van 't Hoff factor for this compound is.
4.
Who said that? Who agrees with him?
I don't know.
I do.
You do? Why do you agree with him?
PO,
Sounds good.
PO4 won't break down. It's
PO4 is
It's
a
its own ion.
polyatomic.
Right. And a polyatomic, likes to hang around together. So there would be the 3 sodiums and the 1 PO4. So the Van 't Hoff factor would indeed be 4. Indeed. Okay. An ideal solution is just like an ideal gas. What is an ideal gas?
Standard temperature and pressure.
Does it exist?
No.
No. Neither does this. All right. For this, you can approximate ideal conditions when the solute and the solvent are very similar. And that is when delta H of solution is equal to 0. How many people remember what goes into calculating the delta H of solution?
Delta H of final minus delta H initial. Dang it.
What about the whole? Doesn't it? It gives you in a chart.
Alright, I'm pulling out my notes from 2 days ago.
Thank you. We'll wait here. Meanwhile, tick tock. This is just time, uploading time. Takes forever to convert these into WAV files.
Oh,
and
did you
then
just add them all together?
add what? Something.
Oh.
Oh. Who was that back there? That was Wasim. Nicely added to the lethargy of.
Alexis.
Or was you first? And then he jumped on the bandwagon? Alrighty. Okay, someone write this moment in time to find delta H1. The amount of energy needed to expand the solute. This is always a endothermic term. Delta H2. The amount of energy needed to expand the solvent. This is also endothermic. Delta H3.
Bless you.
The amount of energy,
It takes to combine them.
okay, that is either released or absorbed when you have a solvent-solute interaction. Mostly this needs to be exo. All right. An ideal solution is going to have delta H1, delta H2, and delta H3 add up to be zippity-doo-dah. Look, it says right in there. Holy cow. All right, if the vapor pressure is greater than expected, greater than calculated, that is called a positive deviation from Raoult's law. Okay, that means that this quantity here is bigger than this quantity here. If this quantity is bigger here, that means that it takes a lot of energy to expand the solute. It does not want to break away from its friends. It takes a lot of energy to expand the solvent. It doesn't want to break away from the friends. And it's not particularly attracted to each other. Okay, so the delta H of solution is endothermic, and it's bigger than delta H3. That is a positive deviation. That means that the vapor pressure is not lowered very much by the solute. If the vapor pressure is less than predicted, that's a negative deviation from the law. That means there's strong solute-solvent attractions. This is a bigger quantity. Okay, so if this is bigger than these two are, that means that the solute and the solvent are hanging around together and they like each other. Okay? And here we go.
So if there's more energy being given off, then that means they're stronger.
That means that the solute and solvent released energy when they combine. Okay, ladies and gentlemen, I am now going to stop this, which means that unfortunately we're going to have two separate files. Oh well.